Right now, somewhere in the world, a power plant is generating electricity for millions of homes. Somewhere, a car engine is running without melting itself. Somewhere, a refrigerator is keeping food cold. Somewhere, desalinated seawater is flowing into a city's water supply. All of these systems, power, propulsion, cooling, water, are powered by one device that most people have never heard of. Engineers call it a heat exchanger. Without heat exchangers, modern industrial civilization as we know it would not function. Not would function less efficiently, would not function. In this video, you are going to understand exactly what a heat exchanger is, how every type works, how engineers mathematically predict their performance, and you are going to see two of the most powerful analysis tools in all of thermal engineering, built from first principles, step by step. This is the deep treatment, the one your textbook could not give you. Welcome to academic engineering.
Here is the problem that every heat exchanger solves. You have two fluids. One is hot, one is cold. You need to transfer heat from the hot one into the cold one. Simple enough. Just mix them, right? You cannot. The two fluids are not compatible. One might be toxic. One might be under different pressure. One might react chemically with the other. One might be the exact product you are trying to keep pure. In a power plant condenser, you are cooling steam with seawater. Mix them, and your entire steam cycle is contaminated with salt. In your car radiator, you are cooling engine coolant with air. The coolant is pressurized. You cannot simply release it. In a refrigeration system, your refrigerant must stay sealed inside the cycle, or it releases into the atmosphere. The engineering challenge is this: transfer as much heat as possible from one fluid to another without the two fluids ever touching. That is what a heat exchanger does. And the wall between the two fluids, that physical barrier that conducts heat while blocking mass transfer, that wall is not just a component. That wall is the engineering achievement.
A heat exchanger is a device that facilitates the exchange of heat between two fluids that are at different temperatures, while keeping them from mixing with each other. Every word in that definition matters. Two fluids, different temperatures, exchange of heat, no mixing. The working principle follows directly from the first law of thermodynamics. Energy is conserved. Whatever heat the hot fluid loses, the cold fluid gains. Every watt that leaves the hot stream enters the cold stream. No heat disappears. Q dot hot equals Q dot cold. This balance is the foundation of every calculation we will do today. Now, the simplest possible heat exchanger is called the double pipe heat exchanger. Imagine two concentric pipes, one inside the other. The hot fluid flows through the inner pipe. The cold fluid flows through the annular space, the ring of space between the two pipes. The inner pipe wall separates them, conducts the heat, but keeps the fluids apart. It is inelegant, it is simple, but it teaches us everything. Because hidden inside this simple device is one of the most important decisions in heat exchanger engineering. Should the two fluids flow in the same direction or in opposite directions? Hold that question. We will answer it mathematically. But first, let us understand every type of heat exchanger that engineers actually use.
There are three fundamental flow arrangements in heat exchangers, and the difference between them is not just engineering preference, it is thermodynamic principle. Parallel flow. In parallel flow, both fluids enter from the same end and travel in the same direction. The hot fluid enters from the left. The cold fluid also enters from the left. They travel together from inlet to outlet. Now watch what happens to the temperature profile. At the inlet, the temperature gap between the two fluids is at its maximum. The hot fluid is at its hottest, the cold fluid at its coldest. But as both fluids travel together, the hot fluid cools, the cold fluid heats, and the gap between them shrinks continuously. By the time they exit, the temperatures have converged. There is a hard limit here. In parallel flow, the cold fluid can never be heated above the outlet temperature of the hot fluid. The two temperature curves are always converging toward each other. They approach, but never cross. Counterflow. Counterflow changes everything. Now, the two fluids enter from opposite ends. Hot fluid enters from the left and flows right. Cold fluid enters from the right and flows left, directly toward the hot fluid's inlet. Now, watch the temperature profile. Something remarkable happens. The cold fluid outlet temperature can exceed the hot fluid outlet temperature. Cold fluid, hotter than the hot fluid at the outlet. That seems impossible until you understand the geometry. Think about what the cold fluid sees as it travels from right to left. It exits on the left side. Where does it find itself? Right next to the hot fluid's inlet. The coldest part of the cold fluid meets the hottest part of the hot fluid. That meeting point is where the cold fluid picks up the most heat. So by the time the cold fluid exits, it has been heated by the hottest section of the hot fluid, and its exit temperature can actually be higher than the hot fluid's exit temperature. This is the counterflow advantage. The temperature driving force, the gap that pushes heat across the wall, is more uniformly distributed along the entire length of the heat exchanger. In parallel flow, the driving force starts enormous and ends small. In counterflow, it stays relatively consistent throughout. And a more uniform, sustained driving force means more heat transfer for the same surface area.
Crossflow. In crossflow, the two fluids flow perpendicular to each other. The classic example is an automobile radiator. Air flows horizontally across the device, while coolant flows vertically through the tubes. Within crossflow designs, we distinguish between mixed and unmixed configurations. If one fluid is confined to channels, tubes for example, its temperature cannot vary across the width of the device. That fluid is unmixed. Each streamline stays at its own temperature. If a fluid flows freely and can mix across its cross-section, it is mixed. Its temperature is uniform at any cross-sectional plane. This distinction matters for the mathematical analysis. Crossflow falls between parallel and counterflow in terms of effectiveness. It is used when the geometry of the application makes full counterflow impractical, as in most air-cooled applications.
We now move from physical understanding to mathematical analysis. But before we write a single equation, we need to make a contract with reality. In engineering, we simplify the world. Not because we are lazy, but because the exact physical truth is mathematically intractable. We make deliberate, justified simplifications, and we know exactly what those simplifications cost us. Here are the 6 assumptions that govern all standard heat exchanger analysis. 1. Steady flow. We assume the temperatures and flow rates do not change with time. This is the steady-state, steady flow approximation. It fails during startup and shutdown, but for normal operating conditions, it is excellent. 2. Negligible kinetic and potential energy. The velocities in a heat exchanger are modest, and elevation changes are small. The energy associated with fluid motion and position is tiny compared to the thermal energy exchanged. We drop those terms from our energy balance. 3. Constant specific heat. We treat the heat capacity of each fluid as constant, independent of temperature. In reality, CP varies slightly with temperature. For most engineering applications, evaluating CP at the average temperature and holding it constant gives excellent accuracy. For fluids with large temperature ranges or phase changes, this requires special treatment.
4. Adiabatic outer surface. The exterior surface of the heat exchanger is perfectly insulated. All heat leaving the hot fluid goes into the cold fluid. None leaks to the environment. In practice, well-insulated HXSs satisfy this almost exactly. 5. First law energy balance. Because of the adiabatic assumption, the heat rate lost by the hot fluid equals the heat rate gained by the cold fluid. This single balance equation connects every temperature in the system. 6. Heat flows from hot to cold. This is simply the second law of thermodynamics. Heat flows spontaneously in the direction of decreasing temperature. It defines our sign convention. Heat transfer rate Q dot is always positive. These assumptions are not weaknesses. They are a carefully designed scaffold that lets us derive closed-form analytical solutions, formulas that actually work in the real world. Now let us build those formulas.
We want to calculate how much heat a heat exchanger transfers. We know Newton's law of cooling at any surface. dq equals U times Th minus Tc times dAs. U is the overall heat transfer coefficient. It accounts for all the thermal resistances between the two fluids. As is the surface area, and Th minus Tc is the local temperature difference between the hot and cold fluids, the driving force for heat transfer. The difficulty is immediately obvious. The temperature difference Th minus Tc is not constant. It changes continuously along the length of the heat exchanger. In parallel flow, it starts large and ends small. In counterflow, it stays more uniform but still varies. So what temperature difference do we use in the overall heat transfer equation? Can we just average the inlet and outlet temperature differences? Try it. Take the arithmetic mean of delta T1 and delta T2. The problem is that arithmetic averaging overestimates the true average driving force. The temperature profiles are curved, not linear. The mean of a curved function is not its arithmetic average. We need the correct mathematical average of the temperature difference along the entire heat exchanger. And to find it, we need to derive it from the physics.
Let us zoom into a tiny differential section of the heat exchanger, an infinitesimally thin slice of surface area, which we call dAs. In this tiny slice, three things are happening simultaneously. First, the hot fluid loses heat. The hot fluid's temperature drops by a tiny amount, dTh, as it passes through this slice. Delta QH equals negative m dot h times CPH times dTh. Note the negative sign carefully. As the hot fluid travels in the positive x direction, its temperature decreases. dTh is negative. The negative sign makes delta QH positive. This is a sign consistency choice, not an error. Second, the cold fluid gains heat. Its temperature rises by dTc. Delta QC equals m dot c times CPC times dTc. Third, the heat flows through the differential surface area following Newton's law. Delta Q equals U times Th minus Tc times dAs. By the first law, all three are equal. Delta QH equals delta QC equals delta Q. Now we combine. From equations 1 and 2, dTh equals negative delta Q over m dot h times CPH. dTc equals plus delta Q over m dot c times CPC. Subtract dTc from dTh to get the change in temperature difference. d of Th minus Tc equals dTh minus dTc equals negative delta Q times 1 over m dot h times CPH plus 1 over m dot c times CPC. Substitute delta Q from equation 3. d of Th minus Tc divided by Th minus Tc equals negative U times dAs times 1 over m dot h times CPH plus 1 over m dot c times CPC. This is a separable ordinary differential equation. The right-hand side is constant along the length of the heat exchanger because U, m dot h, CPH, m dot c, and CPC are all constants by our assumptions. So we integrate both sides from position 1 to position 2. ln of delta T2 over delta T1 equals negative U times AS times 1 over m dot h times CPH plus 1 over m dot c times CPC. Now we use the overall first law energy balance. Q dot equals m dot h times CPH times the total hot side temperature change and equals m dot c times CPC times the total cold side temperature change to substitute and eliminate the capacity rates. After careful rearrangement, Q dot equals U times AS times delta T Lm, where the log mean temperature difference is delta T Lm equals delta T1 minus delta T2
divided by ln of delta T1 over delta T2. This is the LMTD, the log mean temperature difference. It is not an approximation. It is not a convenient average. It is the exact, mathematically rigorous answer to the question, what is the correct mean temperature difference when the driving force varies continuously along the heat exchanger? The calculus gives us this answer directly, and it is a logarithm because the temperature profiles are exponential.
The LMTD formula is the same for both parallel flow and counterflow. Delta TLM equals delta T1 minus delta T2 divided by the natural logarithm of delta T1 divided by delta T2. But the definitions of delta T1 and delta T2 are not the same. Parallel flow, critical definitions. Delta T1 equals TH sub in minus TC sub in, both measured at the same end, the inlet end. Delta T2 equals TH sub out minus TC sub out, both measured at the same end, the outlet end. Counterflow, critical definitions. Delta T1 equals TH sub in minus TC sub out. Hot inlet end, cold fluid is here at its exit. Delta T2 equals TH sub out minus TC sub in. Hot outlet end, cold fluid is here at its inlet. Warning, this is the most common exam error. In counterflow, cold inlet is at the hot outlet end. The confusion arises because the cold fluid in counterflow is flowing in the opposite direction. The cold fluid's inlet is at the same physical location as the hot fluid's outlet. The subscripts refer to temperatures, not to physical positions in the device. You must always draw the temperature profile diagram to verify you are using the correct definitions. Let us apply the LMTD method to a real problem. We will work through a complete industrial thermal design problem, from physical setup to final numerical answer. The scenario is drawn from a food processing plant. A brine solution, our cold stream, enters the heat exchanger at negative 12 degrees Celsius and must be heated to negative 6.5 degrees Celsius. The heating medium is hot water, which enters at 35 degrees Celsius and exits at 20.5 degrees Celsius. Both streams flow through a double-pipe parallel flow heat exchanger, meaning they travel in the same axial direction from inlet to outlet. The hot water flows at a rate of 9 kilograms per minute. The overall heat transfer coefficient for this exchanger is specified as 860 watts per square meter per Kelvin. For the hot water stream, we are given a specific heat capacity of 4.186 kilojoules per kilogram per Kelvin. The engineering objective is clearly stated. Determine the heat transfer surface area A sub S required for this exchanger to deliver the specified thermal duty. This is a classic industrial sizing problem. Before computing anything, we must establish the physical and mathematical model that governs this system. On the left, we define the governing assumptions that underpin this analysis. First, steady-state, steady-flow operation. All fluid properties, flow rates, and temperatures remain constant in time. Second, negligible heat loss to surroundings. The rate of heat released by the hot stream equals exactly the rate of heat absorbed by the cold stream. Third, the specific heat capacity of each fluid is treated as constant over the temperature range of interest. Fourth, the overall heat transfer coefficient U is assumed uniform along the entire exchanger length. Fifth, the energy balance is treated as one-dimensional, varying only along the flow direction. And sixth, this is a parallel flow configuration. Both the hot and cold streams enter from the same end. On the right, we state the governing energy balance. Under our assumptions, conservation of energy requires that the heat lost by the hot stream equals the heat gained by the cold stream. In expanded form, m dot h times Cph times the inlet to outlet temperature drop of the hot stream equals m dot c times Cpc times the temperature rise of the cold stream. This schematic reinforces the physical picture. The hot stream flows left to right, the cold stream flows in the same direction beneath it, and thermal energy Q dot transfers from hot to cold across the separating wall. With the model established, we must choose the correct analytical method. Two standard methods exist for heat exchanger analysis, and selecting the right one depends entirely on what information is known. On the left, the LMTD method. On the right, the NTU effectiveness method. The LMTD method applies when all four terminal temperatures are known, both inlet and outlet for both streams. The NTU method, by contrast, is used when outlet temperatures are unknown. Our problem is a sizing or rating problem. We know what the exchanger must accomplish thermally, and we need the required surface area. The NTU method is better suited to performance prediction problems. The LMTD method allows direct calculation of A sub s without any iteration procedures. The NTU method requires effectiveness charts, or iterative procedures. Physically, the LMTD method is intuitive. It acknowledges that the temperature difference between streams varies continuously along the exchanger length and captures this through a single representative logarithmic mean value. The LMTD method is the preferred approach whenever all four terminal temperatures are specified. The NTU method is not optimal in this situation. The conclusion is unambiguous. Since all four terminal temperatures are fully specified in our problem, the LMTD method yields a direct, closed-form solution for the surface area A sub s. We proceed with this method. We now execute the solution in 5 sequential steps. On the left panel, all given data is recorded: the four terminal temperatures, the overall heat transfer coefficient U, the specific heat C sub P, and the mass flow rate converted to 0.15 kilograms per second. Each of these values will be called upon during the solution. On the right panel, computed results will accumulate as we progress. The center panel is our active workspace. Step 1. Determine the rate of heat transfer. The thermal duty of the exchanger is computed from the hot stream, since its mass flow rate, specific heat, and both temperatures are given. The governing expression is Q dot sub H equals M dot sub H times C sub P times the quantity T sub H in minus T sub H out. Substituting 0.15 kilograms per second multiplied by 4,186 joules per kilogram per Kelvin multiplied by the temperature drop of 35 minus 20.5 degrees Celsius. Q dot sub H equals 9,104.5 watts. This is the thermal duty, the power that must be transferred from the hot stream to the brine. All remaining steps serve to determine what surface area is required to deliver this duty.
Step 2. The temperature difference at the inlet end. In a parallel flow exchanger, both streams enter from the same side. The temperature difference is therefore greatest at the inlet, where the hot stream is warmest and the cold stream is coldest. Delta T1 equals TH in minus TC in, which is 35 minus negative 12. Delta T1 equals 47 degrees Celsius. This is the maximum thermal driving force available anywhere along the exchanger length. Step 3. The temperature difference at the outlet end. As both streams travel through the exchanger, the hot stream cools and the cold stream warms. By the outlet, the temperature gap between them has narrowed significantly. Delta T2 equals TH out minus TC out, which is 20.5 minus negative 6.5. Delta T2 equals 27 degrees Celsius. The driving force has decreased from 47 degrees at the inlet to 27 degrees at the outlet. This spatial variation in temperature difference is the fundamental reason we cannot use a simple arithmetic mean. We require the logarithmic mean. Step 4. The log mean temperature difference, the central quantity of this method. The LMTD is derived by integrating the local heat transfer rate equation along the exchanger length. The result, under the assumptions of constant U and constant specific heats, is delta TLM equals the quantity delta T1 minus delta T2 divided by the natural logarithm of delta T1 over delta T2. This formula is not empirical. It is the exact analytical result of that integration. The logarithm in the denominator applies appropriate weighting. It assigns less influence to the regions where the driving force is smaller. Substituting 47 minus 27 in the numerator and the natural logarithm of 47 over 27 in the denominator. Delta TLM equals 36.1 degrees Celsius. This single value, 36.1 degrees, is the effective mean temperature difference that drives heat transfer across the entire exchanger surface. As expected, it lies between 27 and 47 degrees, weighted toward the smaller value by the logarithmic function. Step 5. Determine the required surface area. We now apply the fundamental heat exchanger design equation. Q dot equals U times AS times delta T LM. Rearranging for the surface area, AS equals Q dot divided by the product of U and delta T LM.
Substituting our computed values, 9,104.5 watts in the numerator and 860 watts per square meter per Kelvin multiplied by 36.1 degrees Celsius in the denominator. A sub S equals 0.293 square meters. The solution is complete. From these, the LMTD method yields the final result directly. Heat exchanger surface area, A sub S equals 0.293 square meters. This result was obtained using the LMTD method, applied to a parallel flow steady-state configuration. From an engineering standpoint, a surface area of less than 1/3 of a square meter is remarkably compact for a heat exchanger delivering over 9 kilowatts of thermal duty. This efficiency reflects the high overall heat transfer coefficient of 860 watts per square meter per Kelvin, characteristic of liquid-to-liquid exchangers with favorable convective conditions on both sides. In practice, a designer would use this surface area, combined with the selected tube diameter and allowable fluid velocity, to determine the required tube length and number of passes. By identifying this as a sizing problem with all 4 terminal temperatures known, we selected the LMTD method, applied it in 5 systematic steps, and arrived at a precise, closed-form answer requiring no iteration and no approximation. This is the power of methodical thermodynamic analysis.
With the first sizing problem complete, we can now turn our attention to a second industrial application. This is the case study 2 on the analysis of heat exchangers. This time, we move from a simple double pipe geometry to something considerably more common in real engineering practice, a compact cross-flow heat exchanger. And the application could not be more familiar, the automotive radiator. The scenario is drawn from automotive thermal management. An automotive radiator operates as a compact cross-flow heat exchanger, with both fluid streams, the hot water and the ambient air, treated as unmixed. That single word carries significant mathematical weight, and we will return to it shortly. The radiator contains 40 tubes, each with an inner diameter of 5 millimeters and a length of 65 centimeters. Hot water, the engine coolant, enters the tube side at 90 degrees Celsius. The water flows at a rate of 0.6 kilograms per second and exits the radiator at 65 degrees Celsius, a drop of 25 degrees, which represents a very specific quantity of heat that the radiator must continuously reject. Air flows perpendicularly across the tube bundle, entering at 20 degrees Celsius and leaving at 40 degrees Celsius. Our task is to determine the overall heat transfer coefficient, U sub I, referenced to the inner surface area of the tubes. The engineering objective is clearly stated. Determine U sub I, the single number that characterizes the combined thermal resistance of this entire heat exchanger, from the hot water inside the tubes to the ambient air flowing across them. This is a classic industrial rating problem. Before computing anything, we must establish the physical picture and the mathematical framework that governs this system. On the left, we define the governing assumptions that make this analysis tractable. First, steady-state, steady-flow operation. All temperatures, flow rates, and fluid properties remain constant in time. The engine is running at a settled operating condition. Second, negligible heat loss to the surroundings. Every joule released by the hot water is received by the air. There is no leakage of energy to the environment outside the exchanger. Third, the water inside the tubes is unmixed. Each tube is an isolated channel. There is no mechanism for water in one tube to exchange energy laterally with water in another. The temperature profile across the tube bundle is discrete, not continuous. Fourth, the air flowing across the fins is also unmixed. The fin structure channels each airstream in a straight path across the radiator. No lateral mixing occurs between adjacent air channels. This is the physical basis for the both fluids unmixed cross-flow classification. And fifth, the specific heat of water is treated as constant, evaluated at the mean bulk temperature of the hot stream. For liquid water over a 25-degree range, this is an excellent approximation. On the right, we state the governing equation that frames the entire analysis. The heat transfer rate equals the product of the overall coefficient, the inner surface area, the cross-flow correction factor F, and the log mean temperature difference referenced to the counterflow arrangement. Written compactly, Q dot equals U sub I times A sub I times F times delta T LMCF.
The correction factor F is not a constant. It is a function of two dimensionless parameters, P and R, which we read from the cross-flow correction factor chart for the both fluids unmixed geometry. This factor accounts for the thermodynamic penalty of the cross-flow arrangement relative to ideal counterflow. The schematic on the right makes the physical arrangement unmistakable. The hot water, shown in red, flows horizontally through the tubes. The cold air, shown in blue, flows vertically across them. These two streams are orthogonal. Heat, Q dot, transfers from the water through the tube walls and into the air. This is crossflow, and it is this geometry that requires the correction factor F. With the model established, we must choose the correct analytical approach. Two standard methods exist for heat exchanger analysis. The choice between them is not a matter of preference. It follows directly from the information available in the problem. On the left, the LMTD method with correction factor F. On the right, the effectiveness NTU method. The LMTD method is applicable when all four terminal temperatures are fully specified, both inlet and outlet for both the hot and cold streams. The NTU method, by contrast, was designed for situations where one or more outlet temperatures are unknown. In our problem, P and R can be computed directly from the given data, without any iteration. The NTU method would require additional cross-flow effectiveness charts, specific to the unmixed geometry, charts that introduce unnecessary complexity here. The correction factor F can be read from the standard cross-flow chart once P and R are known. The LMTD method then provides a closed-form answer for U sub I in a single algebraic step. The NTU method is not structured for this. When the goal is to rate an existing heat exchanger, to determine how well it performs given known operating conditions, the LMTD framework is the natural and most direct tool. The NTU method is better suited to predicting outlet temperatures from a known geometry. The LMTD method with F is the preferred approach for experimental rating problems like this one, where all boundary conditions are measured and the thermal coefficient is the unknown. This is precisely our situation. The conclusion is unambiguous. Because all four inlet and outlet temperatures are fully specified, the LMTD method with the cross-flow correction factor F yields the most direct solution. No iteration, no back calculation, no convergence required. We proceed with this method. We now execute the solution in 5 sequential steps. On the left panel, all given data is recorded. The 4 terminal temperatures of the water and air streams, the tube count, the inner diameter, the tube length, and the mass flow rate of the hot water. Each of these values will be called into service during the solution. On the right panel, computed results will accumulate as we progress through each step. The center panel is our active workspace. Step 1. Determine the total rate of heat transfer.
This is the thermal duty of the radiator, the power it must continuously move from the water to the air. We calculate it directly from the hot stream energy balance, since the mass flow rate, specific heat, and both water temperatures are given. The governing expression is Q dot equals M dot times Cp times the quantity TH in minus TH out. To select the correct specific heat, we evaluate water properties at the mean bulk temperature of the hot stream, the average of 90 and 65 degrees Celsius, which is 77.5 degrees. Standard thermodynamic property tables at this temperature give a specific heat of 4,195 joules per kilogram per Kelvin. Substituting the known operating conditions gives us the full arithmetic. 0.6 kilograms per second times 4,195 times the 25-degree temperature drop. Q dot equals 62,930 watts. Nearly 63 kilowatts of continuous heat rejection. That is a substantial thermal load for a device of this size, and it sets the scale for every calculation that follows. Step 2. The log mean temperature difference, the effective thermal driving potential of the exchanger. The temperature difference between the water and the air is not constant along the length of the radiator. It changes continuously as the water cools and the air warms.
The LMTD is the correct mathematical weighting of this varying driving force. It is the exact result of integrating the local heat transfer equation along the exchanger under the assumption of constant U and constant specific heats. The formula is delta T LMCF equals the quantity delta T1 minus delta T2 divided by the natural logarithm of delta T1 over delta T2. Here, the subscript CF reminds us that the terminal differences are defined using the counterflow convention, which is standard practice before applying the correction factor F. At one end of the exchanger, the water enters at 90 degrees, while the air exits at 40, a terminal difference of 50 degrees Celsius. At the other end, the water exits at 65 degrees, while the air enters at 20, a terminal difference of 45 degrees Celsius. The log mean of 50 and 45 is 47.6 degrees Celsius. Notice how close these two terminal differences are. When delta T1 and delta T2 are nearly equal, the LMTD approaches the arithmetic mean, and 47.6 is almost exactly the midpoint of 50 and 45. This tells us the temperature driving force is remarkably uniform from one end of this radiator to the other. That is the signature of a well-balanced heat exchanger design. Step 3. Determine the inner heat transfer surface area.
The area A sub I is the geometric foundation of the rating equation, the physical interface through which all 63 kilowatts must pass. We compute it as the inner circumference of one tube multiplied by its length, summed across all 40 tubes. A sub I equals N times pi times D times L. Substituting, 40 tubes times pi times 5/1000ths of a meter times 0.65 meters. A sub I equals 0.408 square meters. Pause on that for a moment. Roughly 4/10ths of a square meter of internal tube surface, an area smaller than a standard sheet of drafting paper, is responsible for transferring 63 continuous kilowatts. That compactness is precisely the engineering challenge of radiator design, and it is exactly why the overall heat transfer coefficient must reach such a high value, as we are about to confirm. Step 4. Determine the cross-flow correction factor F. Because this is a cross-flow arrangement rather than pure counterflow, the LMTD computed under the counterflow convention must be adjusted. The correction factor F, always between 0 and 1, captures the thermodynamic penalty of the cross-flow geometry. An F of 1 would mean the exchanger performs identically to ideal counterflow. Any value less than 1 reflects a geometric penalty. F is determined from two dimensionless parameters. As shown on screen, P is the thermal effectiveness of the cold stream, the ratio of the cold side temperature rise to the maximum temperature difference available between the two inlets. R is the ratio of the hot side temperature drop to the cold side temperature rise, reflecting the balance of capacity rates between the two streams. From the given terminal temperatures, P equals 0.36 and R equals 0.80. Entering the correction factor chart for a cross-flow heat exchanger with both fluids unmixed at these coordinates, we read F equals 0.97.
This is an excellent result. A correction factor of 0.97 means the cross-flow geometry here is operating at 97% of the thermodynamic equivalent of ideal counterflow. The geometric penalty is only 3%, a consequence of the well-matched temperature profiles in this particular radiator configuration. Step 5. Determine the overall heat transfer coefficient U sub I. Every quantity the LMTD equation requires is now in hand. Rearranging the governing expression for the unknown, U sub I equals Q dot divided by the product of A sub I, F, and delta T LM CF. Watch each computed result migrate into this final expression: the heat transfer rate from step 1, the inner area from step 3, the correction factor from step 4, and the log mean temperature difference from step 2. 62,930 watts in the numerator, 0.408 times 0.97 times 47.6 in the denominator. U sub I equals 3,341 watts per square meter per degree Celsius. The solution is complete.
Let us consolidate everything the analysis has produced. Overall heat transfer coefficient, U sub I, equals 3,341 watts per square meter per Kelvin. The three supporting results confirm the pathway. an inner surface area of 0.408 square meters, a cross-flow correction factor of 0.97, and a total heat rejection rate of 62.93 kilowatts. The note at the bottom of the screen is worth reading carefully. Airside resistance dominates this heat exchanger completely, and that one observation explains virtually every design decision that goes into a real automotive radiator. Think about what controls U sub I. The overall thermal resistance is the sum of three contributions: convection on the water side, conduction through the tube wall, and convection on the air side. Water, as a liquid, carries convective coefficients comfortably in the range of several thousand watts per square meter per Kelvin. A thin metallic tube wall adds negligible conductive resistance. But air, low density, low thermal conductivity, has forced convective coefficients that are 1 to 2 orders of magnitude below liquid water. The air side is the bottleneck, and it is the air side that pulls the overall coefficient to the value we computed.
This is precisely why every automotive radiator is covered in thin metal fins. Fins exist to compensate for air's poor convective coefficient by dramatically expanding the effective surface area exposed to the airflow. Without fins, the bare tube area of 0.4 of a square meter would be wholly inadequate. With fins, that area multiplies several times over, and the thermal performance of the system becomes viable. The value of U sub I equals 3,341 is not merely a number to record, it is a diagnostic. It tells the engineer exactly where the thermal resistance in this system resides, and therefore exactly where design effort will produce real performance gains. Improving the tube material does almost nothing. Increasing the water side velocity yields diminishing returns, but enhancing the air side geometry through finer fin spacing, optimized fin profiles, or higher airflow velocity attacks the dominant resistance directly. That is the deeper purpose of this analysis. The mathematics gets you to the answer. The physics tells you what to do with it. And carrying that understanding from a calculated number into an informed design decision, that is what distinguishes an engineer from a calculator.
The LMTD method is powerful, but it has a critical limitation. Look at what the method requires. You must know all 4 terminal temperatures, both inlet temperatures, both outlet temperatures. What if you do not know the outlet temperatures? This happens constantly in practice. You have an existing heat exchanger. It has a known size, a known U value, a known surface area AS. Hot fluid enters at a known temperature. Cold fluid enters at a known temperature. You need to know, how much heat does this HX actually transfer? Try applying LMTD. You need delta T1 and delta T2, but those require the outlet temperatures, which are exactly what you do not know. So you guess. Guess TH out. Check the energy balance. Calculate the LMTD. Check if Q dot from energy balance matches Q dot from the LMTD equation. It does not. Guess again. Iterate. This problem, predicting the performance of an existing HX, is called the rating problem. And for the rating problem, LMTD is painful. In the 1950s, engineers developed a method that solves the rating problem directly, with no iteration at all. It is called the NTU method, the number of transfer units method. And it is built on a single, elegant idea: effectiveness.
The key insight of the NTU method is to ask a different question. Instead of how much heat does this HX transfer, ask what is the maximum heat this HX could possibly transfer. If we knew Q dot max, we could define effectiveness as the fraction of that maximum that is actually achieved. Epsilon equals Q dot actual over Q dot max. Effectiveness is dimensionless, bounded between 0 and 1. A perfect HX, infinitely large, has epsilon equals 1. A useless HX has epsilon equals 0. Every real HX falls between these extremes. Now, what is Q dot max? The maximum possible heat transfer would occur if one of the fluids underwent the maximum available temperature change, from its own inlet temperature to the inlet temperature of the other fluid. The maximum available temperature difference in the system is simply TH in minus TC in. But which fluid limits us?
If the hot fluid dropped from TH in all the way down to TC in, it would transfer heat equal to m dot H times CPH times TH in minus TC in. If the cold fluid rose from TC in all the way up to TH in, it would absorb heat equal to m dot C times CPC times TH in minus TC in. These two numbers are not equal in general. The fluid with the smaller heat capacity rate, the smaller product of mass flow rate and specific heat, is the limiting fluid. It is the bottleneck. It reaches its maximum possible temperature change first. Think of it like a relay race. The team's maximum speed is limited by the slowest runner. The fluid with the smaller capacity rate reaches its thermal limit first, and beyond that point, there is no more driving force. The other fluid could accept more heat, but there is nothing left to give. C min equals min of m dot H times CPH, or m dot C times CPC. Q dot max equals C min times TH in minus TC in.
We define two more dimensionless parameters. The number of transfer units, NTU, is a dimensionless size parameter for the heat exchanger. NTU equals U times A sub S divided by C min. A larger NTU means more heat transfer capacity, either because the area is larger, or because U is higher, or because C min is smaller. NTU is the Hx's score in terms of raw size and conductance relative to the limiting fluid's capacity rate. The capacity ratio C is simply the ratio of the smaller to the larger capacity rate. C equals C min divided by C max, always between 0 and 1. From these definitions, the effectiveness can be derived as a function of NTU and C. The derivation follows the same differential approach we used for LMTD, integrated to a closed-form result. The key formulas are: for parallel flow, epsilon parallel equals 1 minus e to the negative NTU 1 plus c divided by 1 plus c. For counterflow, when c is less than 1, epsilon counter equals 1 minus e to the negative NTU 1 minus c divided by 1 minus c times e to the negative NTU 1 minus c. For counterflow, when c equals exactly 1, epsilon counter equals NTU divided by 1 plus NTU, when c equals 1. Let us study these formulas, not just memorize them, but understand what they tell us. Look at the parallel flow formula. As NTU approaches infinity, as you make the heat exchanger infinitely large, what happens to epsilon? The exponential term goes to 0, and the formula approaches 1 divided by 1 plus c. For c equals 1, equal capacity rates, that ceiling is 0.5. You can make a parallel flow heat exchanger the size of a building. You can add surface area without limit. The effectiveness will never exceed 50%. The thermodynamics is working against you. Counterflow has no such ceiling. As NTU approaches infinity with c less than 1, epsilon approaches 1. With enough area, a counterflow Hx can theoretically achieve perfect effectiveness. This mathematically confirms what the temperature profiles showed us intuitively. Counterflow is thermodynamically superior. Now I want to show you something beautiful. Set c equal to 0 in the parallel flow formula. The exponential term simplifies. Set c equal to 0 in the counterflow formula. It simplifies differently, but watch where they both end up. When c equals 0, epsilon equals 1 minus exp negative NTU for all heat exchanger types. Every heat exchanger type, parallel flow, counterflow, crossflow, shell and tube, their different formulas all collapse to the same single expression when c equals 0. What does c equals 0 mean physically? If one fluid is undergoing phase change, condensing steam, boiling water, its temperature stays constant throughout the process. Its effective specific heat is enormous. It absorbs vast amounts of heat at constant temperature. The product m dot times Cp is effectively infinite. C max approaches infinity, so C equals C min divided by C max approaches 0. When one fluid's temperature does not change,
the flow arrangement becomes irrelevant. Whether the other fluid flows parallel or counter or cross, it makes no difference. The physics of phase change dominates everything, and the mathematics knows this. Nature does not distinguish between parallel and counterflow when one fluid cannot change its temperature. The formula knows this. That is beautiful.
With case study 2 behind us, we now encounter a fundamentally different class of heat exchanger problem, one that asks not what a physical device achieves, but what thermodynamics ultimately permits. Case study 3. This is a problem about limits. The scenario involves a counterflow heat exchanger operating under a very specific theoretical condition. Cold water enters the heat exchanger at 10 degrees Celsius, flowing at a rate of 8 kilograms per second. This is the stream being heated. The heating medium is hot water, entering from the opposite end at 70 degrees Celsius at a rate of 2 kilograms per second. The counterflow arrangement means these two streams travel in opposite directions, the most thermodynamically efficient geometry available for any two-fluid heat exchanger.
The specific heat of water is taken as constant at 4.18 kilojoules per kilogram per Kelvin, applied uniformly to both streams. The question being posed is a profound one. Determine the maximum heat transfer rate this system can theoretically achieve, and identify the corresponding outlet temperatures of both streams. The engineering objective is clearly stated. Find Q dot max and the outlet temperatures of both the cold and hot streams. Notice that no surface area is given. No overall heat transfer coefficient is specified. That is entirely intentional, and it is the key to understanding what makes this problem special. Before we compute anything, we need to establish precisely what physical situation we are analyzing, because this case study rests on a concept that is more subtle than it first appears. On the left, we define the assumptions that frame this analysis. First, steady-state operation. All temperatures and flow rates are constant in time. The exchanger has reached its settled operating condition. Second, a well-insulated casing, meaning heat loss to the surroundings is zero. Every joule that leaves the hot stream enters the cold stream. The system is thermally isolated from its environment. Third, constant specific heat values for both streams. With a single value of 4.18 applied to both water streams, the heat capacity rates become simple products of mass flow rate and specific heat. Fourth, and this is the assumption that defines this entire problem, the exchanger is treated as infinitely long. We are not analyzing a real physical device with a finite surface area. We are asking, if this heat exchanger could be made as large as we wished, what is the absolute maximum heat transfer the laws of thermodynamics would allow? This is the limiting case, where surface area A approaches infinity. And fifth, counterflow arrangement. The two streams flow in opposite directions. This is critical because counterflow is the only configuration that can, in principle, approach the thermodynamic limit we are about to describe.
On the right, we state the governing equation for this limiting scenario. The maximum heat transfer rate equals the minimum heat capacity rate of the two streams, multiplied by the maximum temperature difference available between them. Written compactly, Q dot max equals C min times delta T max. The maximum temperature difference is simply the difference between the two inlet temperatures, the hottest point of the hot stream and the coldest point of the cold stream. This is the largest driving potential the system possesses anywhere along its length. The schematic on the right captures the physical arrangement precisely. The hot stream, in red, flows from left to right. The cold stream, in blue, flows from right to left. They are countercurrent. The heat Q dot transfers continuously from the hot stream to the cold stream across the separating wall. In the limiting case, one of these streams will exhaust its temperature potential completely, and that stream is always the one with the smaller heat capacity rate.
This problem demands a specific analytical approach, and understanding why is just as important as knowing which method to use. Two analytical frameworks are available. On the left, the capacity rate limiting analysis, built around the concept of C min. On the right, the LMTD method, which we applied in the previous two case studies. Let us examine why the LMTD method, despite its power, is simply not the right tool here.
The capacity rate limiting approach is explicitly designed to identify the maximum thermodynamic potential of a heat exchanger system. The LMTD method, by contrast, requires all 4 terminal temperatures to be known before it can compute the log mean temperature difference. And in this problem, the outlet temperatures are precisely what we are trying to find. The capacity rate method finds the theoretical limit by identifying which stream, hot or cold, has the smaller heat capacity rate, Cmin. It is that stream which will reach the inlet temperature of the other stream first as the exchanger length increases. The LMTD method has no mechanism to identify this limiting stream directly. Crucially, the capacity rate analysis requires no knowledge of the physical surface area. Q dot max is computed directly from the inlet temperatures and mass flow rates alone. The LMTD method, however, is fundamentally coupled to the physical surface area through the relation Q equals U times A times delta TLM, and no area is given here.
Furthermore, in the true limiting case where A approaches infinity, the LMTD method breaks down entirely. As the exchanger becomes infinitely long, one terminal temperature difference approaches 0, and the logarithm in the LMTD formula becomes singular. The method cannot handle this limiting geometry. The capacity rate approach is immune to this difficulty. It is built precisely for this scenario. The capacity rate method requires only mass flow rates and inlet temperatures, exactly and completely the information we have been given. The LMTD method would require additional information we do not possess. The conclusion is unambiguous. Because this problem focuses on the theoretical limit where A approaches infinity, we must calculate Cmin and apply the capacity rate limiting analysis directly. No other approach is appropriate. The workspace is now organized. Given data on the left, the solution developing its center, results accumulating on the right. 5 steps will take us from the raw given information to the complete answer. On the left panel, our complete given information is recorded. The hot water inlet temperature of 70 degrees, the cold water inlet temperature of 10 degrees, the hot stream mass flow rate of 2 kilograms per second, the cold stream mass flow rate of 8 kilograms per second, and the specific heat of 4.18 kilojoules per kilogram per Kelvin. Every one of these values will be called into service during the solution. Step 1. Determine the heat capacity rates of both streams. The heat capacity rate is the product of mass flow rate and specific heat. It tells us how much thermal power a stream gains or loses per unit temperature change. It is the single most important quantity in the thermodynamic limit because the stream with the smaller capacity rate is the one that will reach its temperature limit first. The governing expressions are CH equals m dot H times Cp and Cc equals m dot C times Cp. For the hot stream, 2 kilograms per second times 4.18 kilojoules per kilogram per Kelvin gives CH equals 8.36 kilowatts per Kelvin. For the cold stream, 8 kilograms per second times 4.18 gives Cc equals 33.44 kilowatts per Kelvin. The hot stream carries a capacity rate of 8.36. The cold stream carries 33.44. The hot stream is clearly the limiting stream. Cmin equals 8.36 kilowatts per Kelvin. This result is physically meaningful. The hot stream has a much lower mass flow rate than the cold stream, and since both streams share the same specific heat, the hot stream simply cannot supply heat at the same rate that the cold stream could absorb it. The hot stream is the bottleneck, and it will be the one to reach the inlet temperature of the cold stream first as the exchanger length increases. Step 2. Determine the maximum available temperature difference. In a counterflow heat exchanger operating at the thermodynamic limit, the maximum temperature difference that drives heat transfer is simply the difference between the 2 inlet temperatures, the hottest point available in the system and the coldest point available. The expression is delta T max equals TH in minus TC in. Substituting 70 minus 10. Delta T max equals 60 Kelvin. 60 degrees of temperature potential. This is the full thermodynamic resource available to this system. It represents the absolute maximum temperature difference that could ever drive heat transfer between these 2 streams, and it occurs at the inlet ends of a counterflow arrangement.
Step 3. Compute the maximum heat transfer rate. With Cmin and delta T max both established, the maximum heat transfer rate follows directly from the fundamental capacity rate equation. Q dot max equals Cmin times delta T max. 8.36 kilowatts per Kelvin
multiplied by 60 Kelvin. Q dot max equals 501.6 kilowatts. Over half a megawatt of heat transfer. This is the absolute ceiling imposed by thermodynamics on this particular system, regardless of how large the heat exchanger is made. No physical device, however well designed, can exceed this value for these inlet conditions and flow rates. It is a hard limit, set not by engineering, but by the second law of thermodynamics. Step 4. Determine the outlet temperature of the cold stream. Now that Q dot max is known, we can apply the steady-state energy balance to each stream individually to find the outlet temperatures. For the cold stream, the outlet temperature is the inlet temperature plus the heat absorbed divided by the heat capacity rate. Tc out equals Tc in plus Q dot max divided by Cc. 10 degrees plus 501.6 divided by 33.44. Tc out equals 25 degrees Celsius. The cold stream is heated from 10 degrees to 25 degrees, a rise of 15 degrees. This is a modest temperature gain, and it makes physical sense. The cold stream has a very large heat capacity rate, 33.44 kilowatts per Kelvin, meaning it takes a great deal of thermal energy to move its temperature by even 1 degree. Even absorbing 500 kilowatts, the cold stream temperature rises by only 15 degrees. That is the signature of a high-capacity rate stream.
Step 5. Determine the outlet temperature of the hot stream. Applying the same energy balance to the hot stream, the outlet temperature is the inlet temperature minus the heat released divided by the heat capacity rate of the hot stream. Th out equals Th in minus Q dot max divided by Ch. 70 degrees minus 501.6 divided by 8.36. Th out equals 10 degrees Celsius. The hot stream exits at exactly 10 degrees, the inlet temperature of the cold stream. This is not a coincidence. It is the definition of the thermodynamic limit for the C-min stream. In a counterflow arrangement with infinite surface area, the stream with the smaller heat capacity rate, the hot stream in this case, will cool all the way down to the inlet temperature of the other stream. It has exhausted its entire temperature potential. There is nothing left to give. The solution is complete. Let us consolidate what the analysis has produced. Maximum heat transfer rate and outlet temperatures. Q dot max equals 501.6 kilowatts. Tc out equals 25 degrees Celsius. Th out equals 10 degrees Celsius. These three numbers together tell a complete physical story. The hot stream enters at 70 degrees and exits at 10. It has been cooled all the way to the inlet temperature of the cold stream, surrendering every degree of thermal potential it possessed. The cold stream enters at 10 and exits at 25. It has absorbed 500 kilowatts, but its large heat capacity rate means that enormous energy transfer produces only a moderate temperature rise. And the maximum heat transfer rate of 501.6 kilowatts is the thermodynamic ceiling, the absolute limit that no real physical device operating with these two streams and these inlet conditions can ever exceed.
This is the power and the elegance of the capacity rate limiting analysis. It bypasses the need for surface area, overall heat transfer coefficient, and geometry entirely. It goes directly to the thermodynamic heart of the problem, asking what the laws of physics ultimately permit before any engineering decisions are made about how to build the device. In practice, an engineer uses this result as the design benchmark. The actual heat exchanger, with its finite surface area and real overall heat transfer coefficient, will always perform somewhere below this ceiling. The closer to the limit it operates, the more thermodynamically efficient the design. The ratio of actual heat transfer to Q dot max is precisely the definition of heat exchanger effectiveness, the central concept of the NTU method that we will encounter in future case studies. What this problem teaches, above all, is that engineering analysis has two distinct modes. The first asks, given a physical device, what does it do? The second asks, given the laws of thermodynamics, what is the best any device could ever do? This case study belongs firmly to the second category, and the ability to think in those terms, to reason from first principles about thermodynamic limits before worrying about physical design, is one of the most valuable habits an engineer can develop.
With the thermodynamic limits of case study 3 established,
We now encounter a problem that bridges theory and physical design, a problem where we know what the heat exchanger must accomplish, but need to determine how large it must be to accomplish it. Case Study 4. This is a sizing problem, and it introduces the most powerful analytical framework in heat exchanger analysis, the effectiveness NTU method. The scenario involves a counterflow double-pipe heat exchanger drawing on a geothermal energy source. Cold water enters the heat exchanger at 20 degrees Celsius and must be heated to 80 degrees Celsius, flowing at a rate of 1.2 kilograms per second, a 60-degree temperature rise, a significant thermal demand. The heat source is geothermal hot water, entering at a very high temperature of 160 degrees Celsius at a flow rate of 2 kilograms per second. Notice that only the inlet temperature of the hot stream is specified. Its outlet temperature is unknown, and that single missing piece of information is precisely what makes this problem the natural domain of the NTU method. The inner tube is thin-walled with a diameter of 1.5 centimeters. The overall heat transfer coefficient U is 640 watts per square meter per Kelvin, a value that reflects the combined convective performance of both fluid streams.
The problem explicitly prescribes the method. Use the effectiveness NTU approach to determine the required length of the heat exchanger. This is not merely a suggestion, it is an instruction that tells us precisely which analytical path leads to the answer with the least effort. The engineering objective is clearly stated. Find L, the length of tube required for this counterflow heat exchanger to deliver the specified thermal duty. Everything else, the surface area, the effectiveness, the NTU, are intermediate quantities that build toward this final answer. Before any calculation begins, we establish the physical and mathematical model that governs this system. On the left, we define the assumptions that frame the analysis. First, steady state, steady flow operation. All temperatures, flow rates, and fluid properties are constant in time. The system has reached its settled operating condition. Second, a well-insulated shell, meaning heat loss to the surroundings is zero. All thermal energy released by the geothermal water is absorbed by the cold water. There is no leakage to the environment. Third, constant fluid properties for both streams. The specific heat of the cold water is 4.18 kilojoules per kilogram per Kelvin. The geothermal hot water, at its elevated temperature range, carries a slightly different specific heat of 4.31, a distinction we will account for carefully in the calculation. Fourth, the inner tube is thin-walled, meaning the inner and outer diameters are essentially equal. We use a single diameter d throughout, which simplifies the area calculation at the end. And fifth, negligible thermal conduction resistance through the tube wall itself. For a thin metallic wall, the conductive resistance is orders of magnitude smaller than the convective resistances on either side, and it can be safely ignored. On the right, we state the governing equations that frame the analysis. The actual heat transfer rate is computed from the cold stream energy balance. Q dot equals m dot sub c times CPC times the temperature rise of the cold stream from its inlet to its outlet. The maximum possible heat transfer rate, the thermodynamic ceiling we encountered in case study 3, is C min multiplied by the difference between the two inlet temperatures. This is the reference value against which the actual performance will be measured. The schematic confirms the counterflow arrangement. Geothermal hot water, shown in red, flows from left to right. Cold water, shown in blue, flows in the opposite direction, from right to left. Heat Q dot transfers continuously from the hot stream to the cold stream across the tube wall. This opposing flow direction is what makes counterflow the most thermodynamically efficient configuration, and it is what allows the analytical expressions for the NTU method to take their most compact and elegant form. The problem statement has already told us which method to use, but understanding why that instruction is correct is more valuable than simply following it. Two standard frameworks are available. On the left, the effectiveness NTU method. On the right, the LMTD method.
Let us work through the comparisons systematically. First, the problem explicitly requests the effectiveness NTU method. That alone is a sufficient instruction in an engineering context, but the reasons behind that instruction are worth understanding. The LMTD method, by contrast, would require us to first determine the geothermal outlet temperature, TH out, before we could compute the log mean temperature difference. That temperature is not given. Second, the NTU method does not require the hot side outlet temperature. It works entirely from inlet temperatures, flow rates, specific heats, and the known cold side outlet temperature. The LMTD approach cannot even begin until TH out is found, which requires an additional energy balance calculation as a prerequisite step. Third, the effectiveness NTU framework directly connects the thermodynamics to the sizing parameters. Once the effectiveness is computed and the NTU is extracted from the analytical relation, the required surface area follows immediately. The LMTD method requires more intermediate steps to reach the same endpoint. Fourth, for a counterflow heat exchanger, the NTU method has a clean closed-form analytical expression relating effectiveness, NTU, and the capacity rate ratio. There is no iteration, no chart reading uncertainty, no approximation. A single equation delivers the NTU directly. And fifth, the effectiveness NTU method is inherently well-suited to design and sizing analysis of this type, where a desired thermal outcome is specified and the required physical size must be determined. This is precisely the structure of our problem. The conclusion is straightforward. The epsilon NTU method allows us to solve directly for the required heat exchanger surface area and length efficiently, analytically, and without any intermediate iteration. We proceed with this method.
The workspace is now organized into 3 panels. Given data on the left, the solution developing at center, results accumulating on the right. 5 steps carry us from raw data to the required tube length. On the left panel, our complete given information is recorded. The hot and cold inlet temperatures, the cold outlet temperature, the mass flow rates of both streams, the tube diameter, the overall heat transfer coefficient, and the specific heats of both the cold water and the geothermal hot water. 2 different specific heats. This is a detail that matters, and we will use each one in its correct place. Step 1. Determine the heat capacity rates of both streams and their ratio. The heat capacity rate of each stream, the product of its mass flow rate and specific heat, governs how much thermal power it can carry per unit temperature change. The ratio of the smaller to the larger capacity rate is a dimensionless parameter C that appears directly in the NTU formula for counterflow exchangers. The governing expressions are C sub H equals m dot H times Cp sub H, and C sub C equals m dot C times Cp sub C. For the geothermal hot stream, 2 kilograms per second times 4.31 kilojoules per kilogram per Kelvin gives C sub H equals 8.62 kilowatts per Kelvin. For the cold water stream, 1.2 kilograms per second times 4.18 gives C sub C equals 5.02 kilowatts per Kelvin. The cold stream has the smaller capacity rate. C min equals 5.02 kilowatts per Kelvin. The capacity rate ratio, C, equals C min divided by C max, which is 5.02 divided by 8.62, giving C equals 0.582. This ratio tells us something immediately useful. A C value of 0.582, well below unity, means the 2 streams are moderately mismatched in their thermal capacity. The cold stream will change temperature more rapidly than the hot stream per unit of heat transferred, and it is the cold stream that defines the thermodynamic limit of this system.
Step 2. Determine both the maximum and the actual heat transfer rates. These 2 quantities together define the effectiveness, the central dimensionless parameter of the NTU method. The maximum heat transfer rate is C min multiplied by the full inlet-to-inlet temperature difference, 5.02 times the quantity 160 minus 20. Q dot max equals 702.8 kilowatts. This is the thermodynamic ceiling, the most heat this system could transfer if the exchanger were infinitely long. The actual heat transfer rate is what the exchanger is designed to deliver, computed from the cold stream energy balance using its known inlet and outlet temperatures, 1.2 times 4.18 times the quantity 80 minus 20. Q dot actual equals 301 kilowatts. The heat exchanger delivers 301 kilowatts of the 702.8 kilowatts theoretically available. The ratio of these 2 numbers is the effectiveness, and that is exactly what we compute next. Step 3. Compute the heat exchanger effectiveness. Effectiveness is the ratio of actual heat transfer to the thermodynamic maximum.
It is a dimensionless measure of how efficiently the heat exchanger exploits the available temperature potential, bounded between 0 and 1, where 1 represents the theoretical ideal of infinite surface area within the system. The expression is simply epsilon equals q dot actual divided by q dot max, 301 divided by 702.8. Epsilon equals 0.428, or 42.8%. This is a moderate effectiveness. The heat exchanger is capturing roughly 43% of the maximum possible heat transfer from this geothermal source. It is not a highly effectiveness optimized design, but it does not need to be. It needs to be exactly large enough to heat the cold water from 20 to 80 degrees, and that is precisely what the remaining steps will establish.
Step 4. Determine the number of transfer units, NTU. The NTU is a dimensionless measure of the heat exchanger's thermal size. A large NTU means a physically large exchanger with high heat transfer capacity. A small NTU means a compact exchanger. The NTU encapsulates the combined effect of the surface area, the overall heat transfer coefficient, and the minimum capacity rate, all in one dimensionless number. For a counterflow heat exchanger, the analytical relation between NTU, effectiveness, and the capacity rate ratio C is NTU equals 1 over the quantity C minus 1, multiplied by the natural logarithm of the quantity epsilon minus 1, divided by the quantity epsilon times C minus 1. Substituting C equals 0.582 and epsilon equals 0.428 into this expression, NTU equals 0.651. A relatively modest NTU, consistent with a moderate effectiveness of 43%. This single number now connects the thermodynamics directly to the physical geometry through the definition NTU equals U times A sub S divided by C min. All that remains is to rearrange that definition to find the required surface area and, from the geometry, the required length. Step 5. Convert the NTU into physical dimensions, surface area, and tube length. From the definition of NTU, the required heat transfer surface area is A sub S equals NTU times C min divided by U, and the tube length follows from the geometry of a single cylindrical tube, L equals A sub S divided by pi times D. For the surface area, 0.651 multiplied by 5.02 kilowatts per Kelvin, converted to watts per Kelvin, divided by 640 watts per square meter per Kelvin. A sub S equals 5.11 square meters. For the length, 5.11 divided by pi times 0.015 meters. L equals 108 meters. The solution is complete. 108 meters of tube, nearly the length of a football field, is required to heat this cold water stream from 20 to 80 degrees using the available geothermal source. Let us bring the complete solution together. Required heat exchanger length, L, equals 108 meters. The required surface area is 5.11 square meters, achieved through 108 meters of tube with an inner diameter of 1.5 centimeters. 108 meters. To a student encountering this result for the first time, it can seem surprisingly large, but consider what it reveals about the physics. The overall heat transfer coefficient of 640 watts per square meter per Kelvin is a reasonable value for liquid-to-liquid forced convection in a small tube. But the minimum capacity rate of only 5 kilowatts per Kelvin means the system requires relatively few transfer units to achieve a 43% effectiveness. The length is large, not because the heat transfer is inefficient, but because the tube diameter is small. 5.11 square meters of area distributed over a 15-millimeter tube simply demands a long run of pipe. In practice, this length would never be realized as a single straight pipe. It would be coiled, folded into multiple passes, or implemented as a shell and tube configuration with many tubes in parallel, each of which would reduce the required length per tube proportionally. The 108-meter figure is the fundamental thermal sizing result. The mechanical packaging is a separate engineering decision. This case study also illustrates the full power of the epsilon NTU method as an analytical tool. Starting from nothing more than 2 inlet temperatures, 2 flow rates, 2 specific heats, a tube diameter, and an overall heat transfer coefficient, we extracted the effectiveness, the NTU, the surface area, and finally the physical length, all without once needing to know the geothermal outlet temperature and without any iteration whatsoever.
The method is not just convenient, it is structurally the right tool for this class of problem, and developing the intuition to recognize when to reach for it rather than defaulting to LMTD is one of the marks of a mature heat transfer engineer. The mathematics, as always, is the servant of the physics, and the physics, understood clearly, makes every step of the mathematics feel inevitable.
For completeness, here is the full NTU effectiveness reference table covering all major heat exchanger configurations. Each formula was derived using the same differential equation approach we used, just with the appropriate geometry and flow path integrated in. This table should be in your formula sheet for every exam and every engineering calculation. Now that you have built all of this from first principles, let us talk about the traps. These are the 6 most common errors that students make, and they are precisely the errors that derivation-level understanding eliminates. Misconception 1. Delta T definitions. The error: students use delta T1 equals TH in minus TC in for both parallel and counterflow. The truth: in counterflow, delta T1 equals TH in minus TC out. Cold outlet is at the hot inlet end. The cold fluid is flowing in the opposite direction. If you drew the temperature profile diagram, you cannot make this error. If you memorize the formula without drawing, you will. Misconception 2. Natural log versus log base 10. The error: students use log base 10 in the LMTD formula. The truth: always natural log, ln. The derivation showed this clearly. We integrated d of delta t over delta t, which gives ln of delta t. The natural log emerged from the calculus itself. It is not a convention choice. Misconception 3. C-min identity. The error: students assume C-min is always the cold fluid. The truth: C-min is whichever fluid has the smaller product of mass flow rate and specific heat, m dot times Cp. This could be either the hot or cold fluid. Always compute both capacity rates and compare.
Misconception 4. Parallel flow effectiveness ceiling. The error: students believe that adding enough surface area to a parallel flow HX will eventually achieve epsilon equals 1. The truth: for parallel flow, epsilon is always bounded above by 1 over 1 plus c, which is always less than or equal to 0.5. No amount of surface area breaks this ceiling. This is a thermodynamic constraint, not a practical limitation. Misconception 5. C equals 0 meaning. The error: students believe C equals 0 means no fluid is flowing. The truth: C equals 0 means one fluid is undergoing phase change. During condensation or evaporation, the fluid's temperature is constant. Its effective specific heat is enormous. C max approaches infinity, so C equals C min over C max approaches 0. Misconception 6. When to use LMTD versus NTU. The error: students try to apply LMTD when outlet temperatures are unknown, leading to iteration. The LMTD is for design problems. All 4 terminal temperatures known, find A sub s. NTU is for rating problems. HX size known, inlet temperatures known, find Q dot and outlet temperatures. Choosing the wrong method wastes time. Choosing the right one gives the answer in one calculation. Let me show you how everything we have covered fits together. We began with a physical problem: transfer heat between 2 fluids without letting them mix. The heat exchanger is the engineering solution. The flow arrangement determines the temperature profile, and parallel flow is thermodynamically limited in a way counterflow is not. The 6 assumptions clean up the mathematics and let us derive closed-form solutions. The LMTD method tells us, given all 4 terminal temperatures, here is the required surface area, or here is the heat transfer rate. Q dot equals U times AS times the log mean temperature difference. The NTU method tells us, given the HX size and inlet conditions only, here is the actual heat transfer rate, with no iteration. Effectiveness equals actual divided by maximum possible heat transfer. And hidden inside the NTU method is a mathematical jewel. When C equals 0,
When one fluid is undergoing phase change, every flow arrangement collapses to the same formula. Epsilon equals 1 minus e to the negative NTU. The physics of phase change is so dominant that nothing else matters. The condenser outside your home, the radiator in your car, the heat recovery system in a gas turbine, they all obey this mathematics. You now know their physics.
You now understand heat exchangers, not as a list of formulas to memorize, but as a coherent engineering discipline with physical intuition, mathematical rigor, and real-world relevance. You can classify every type by construction and flow arrangement. You know why counterflow is superior, and you can prove it with the LMTD comparison. You can apply 2 different analysis methods and know which one to reach for depending on what is given. You have seen a beautiful mathematical result, the C equals 0 collapse, that no textbook pauses to appreciate. Every condenser, every radiator, every feed water heater, every oil cooler you encounter in your career, you know its physics now. This has been academic engineering. If this video gave you that clarity, that feeling that something finally makes complete sense, then subscribe. Because every topic we cover like this. See you in the next one.